Hello everyone. Today we have lecture 38 and topic we will continue our discussion on oxidation of metals and alloys, and today we will talk mainly Eulers diagram. Now, if you see in the last class we have seen a relation between standard free energy change for oxidation of pure metal forming pure oxide, and that too stoichiometric oxide, and that free energy change at standard state is equal to minus RT ln K. K is the equilibrium constant, or equal to RT ln PO2 to the power n. So, this PO2 to the power n could be 1 or could be half or could be some fraction depending on how the reaction oxidation reaction is taking place. So, now in the last class we have come across this important relation when an oxidation reaction reaches equilibrium, which is RT, this is minus RT ln PO2 to the power n. So, this n is 1 when oxidation reaction is like this, or m plus O2 equal to M2O. So, this is in both the cases I will have n equal to 1. N would be half when we write the equation like half O2 equal to MO, n equal to 3 by 2 when we write M plus O2 equal to M2O3. So, that case n becomes 3 by 2. So, like that way n would vary. Now, from this equation we could get to know that PO2 what you are getting here is equilibrium partial pressure of oxygen at temperature where we are carrying out the oxidation, and this temperature is fixed temperature. So, that means, and at the same time since delta G0 is a function of temperature only as well as K is a function of temperature only. So, that is what this partial pressure of oxygen becomes equilibrium partial pressure at that temperature. Now, at the same time we have experienced that if we plot delta G0 with 1 by T, we get a plot like this, and then we have to stay down this way when that time we get M plus O2, and if we go that direction then we have MO2. That also we have seen at a particular temperature. Let us say if this is the temperature we are considering, beyond this line we have MO2 to be stable, because the partial pressure of oxygen at that temperature which is in equilibrium for the reaction, and here we are taking this reaction and say, and that time this beyond this line partial pressure of oxygen which is actual is greater than PO2 equilibrium temperature, and this is the temperature what we are considering. And if we go downwards, here we get, this is the have a situation PO2 actual less than PO2 equilibrium temperature. So, in this case at that temperature system always would like to attain equilibrium if it is a closed system, and then in order to achieve this equilibrium partial pressure of oxygen at that temperature, metal oxide would reduce to form more amount of oxygen. But in this case, since this is more than this equilibrium partial pressure of oxygen, more amount of oxidation would take place. That information we had. Now, then we realize that we have also started talking about Illingham diagram. We just mentioned that next class will be doing analysis on the basis of Illingham diagram. So, in order to do Illingham diagram, let us see how del G T at a temperature. So, this temperature I am talking about is related to del H 0 T minus T del S 0, or this is 0 or not. So, this equation I can write. Okay. Now, del H, this one can be written as from the Kirchhoff's law, this we can get. At the same time we can also get del S and this del Cp is the difference between product minus reactant, the Cp of product minus Cp of reactant, that is the del Cp. So, now we get this, and Cp is having a function of temperature which is a kind of polynomial function of temperature, which can be written as like that. Now, if this is these are constants, and then I can write del Cp equal to del A plus del B T plus del C T to the power minus 2. So, that means I could see that this particular value, that is del G T naught, is having a complex relation with temperature. Now, that means I would also say that if I try to plot del G T with temperature, I will have a non-linear plot. Non-linear plot. But H J T Illingham, he has shown in 1944 and he has also shown that in a paper which titled Reducibility of Oxides and Sulfides in Metallurgical Processes, which was published in Journal of Society of Chemical Industries, and there he mentioned that del G, this factor, this value, which is the free energy change in standard state at a particular temperature for oxidation process, can be written as this form. Okay, that can be written as this form. So, that means if I see this form, so and where A equal to del H 0, B equal to del S 0 with a minus sign. So, for oxides as well as for sulfides, since we are talking about oxidation, so we will talk about oxides. So, del G naught T has linear relation with temperature, provided condition, this is a linear relation, linear relation. So, now provided there is no change in state, change in state means it remains solid all the time or it remain liquid all the time, any species. For example, if I consider M plus O2 equal to MO2, this is solid, this is solid, this is gas. So, this will remain solid, this will remain solid, this will remain gas. So, there will be no state change. So, that case over a temperature range, this linear relation can be true. Now, this is the standard entropy change, this is the enthalpy change, standard enthalpy change. And now, since this is a simple linear equation, if I take oxidation process, this process, I can write del H 0 to be H 0 MO2 S minus H 0 M S minus H 0 O2 G. This is del H 0, and del S 0 can be written as this is the product, these two are reactants. So, now S 0 MO2 which is solid, this is entropy, minus S naught M S minus S naught O2 gas. Now, if we see the value of these two quantities, they are almost equivalent since they are solid state, their entropy is very low. But if I try to see this entropy in comparison to these two entropies, so I can say that this value is very large as compared to or S 0 MO2 solid. So, that can allow me to have a kind of approximation this approximation is possible because of this situation, and then I could see that the entropy of gas is always positive and there is a negative sign in front of it. So, this becomes negative, and when I take B, since B is minus del S 0, so then B becomes positive because this becomes negative. So, there is a negative sign, this becomes negative from this relation, and since there is a negative sign, so it becomes positive. So, that means the slope of this linear plot is positive. So, if I try to plot, let us say taking an example, and this example is taken from Gaskell, the book by Gaskell. So, there it is taken as Ag oxidation. So, this oxidation is taken, this reaction, and there if you plot temperature with del G T, which is nothing but R T ln PO2, and since it is a linear A plus B T mode. So, this relation becomes like this, and now it has a 0 value minus 10 kilojoule per mole, and here it is minus 20 kilojoule per mole of oxygen. Now, here if I draw a parallel line with T at 0 value, so this is 10, this is 20, and here of course is a minus sign, this is plus 0 value. So, this value indicates PO2 to be 1 atmosphere, and this is also equilibrium temperature at that temperature, and now this point is the equilibrium temperature. So, this is T equilibrium and here it is 4 62 Kelvin. So, at this temperature when this del GT line this line is drawn like this, wherever it cuts that point belong to PO2 equilibrium at temperature. So, this temperature I can write as 462 Kelvin. So, now delta Z0 T equal to 0, which is nothing but for this equation RT ln PO2, hence PO2 equal to 1 atmosphere. Okay, so, this is the equilibrium partial pressure. Now, if I go at a temperature let us say T which is less than 462 Kelvin. So, that time delta Z0 T is less than 0, which means that PO2 equilibrium temperature, which is let us say T prime. So, this is T prime should be less than PO2 equilibrium at 462 Kelvin. Now, interesting part is this any point on this line, this particular line, any point is indicating equilibrium standard free energy change at that temperature. So, that also indicates equilibrium partial pressure of oxygen. Now, if I take Ag, Ag2O and O2 in a closed system, and then if I keep it at 462 Kelvin and if I maintain O2 as 1 atmosphere, then this system will be at equilibrium, because I know if this is a closed system, that means if PO2 is maintained as 1 atmosphere pressure, and at the same time we will also know that PO2 equilibrium at 462 Kelvin is 1 atmosphere. So, that time pure Ag2O as well as O2 will be in equilibrium. Now, this particular system, if the temperature sorry T prime since the P equilibrium PO2 at equilibrium at T prime is less than 1 atmosphere. So, that times you have more oxygen than the required equilibrium partial pressure of oxygen at T prime. So, Ag will oxidize and form Ag2O. So, that means here if I go to T prime at this location, if I start from this location, I will have more oxidation of Ag. Now, similarly, if I consider temperature, let us say I take a temperature T double prime, this is the point where it reaches equilibrium. So, at this location delta G 0 T double prime and here it is T prime greater than 0, because this is the 0 value and corresponding value is greater than 0 and here corresponding value was less than 0. So, then of course, PO2 equilibrium at T double prime should be greater than PO2 equilibrium at 462 Kelvin. Now, similarly, if I start with a system where I have pure Ag2O and O2 at 1 atmosphere pressure, that partial pressure of oxygen is 1 atmosphere, that time it reaches equilibrium. But once I take this temperature to T double prime, that means this temperature, this point it is taken to this particular point, then I see that the requirement for PO2 to reach equilibrium for that reaction, this reaction is more than 1 atmosphere pressure. But in the closed system we are not supplying any oxygen from outside. So, how does it get oxygen, extra oxygen to reach equilibrium? So, that time Ag2O will convert to Ag plus O2. So, this reaction, the reverse reaction will start. So, that time I could say that Ag2O becomes unstable and it will reduce. So, there are three situations rather. If we have a closed system where we have these three species and oxygen partial pressure is 1 atmosphere, system will reach equilibrium and that equilibrium temperature is 462. Now, this equilibrium system is taken to, one time it is taken to T prime which is less than 462. So, that time I could see that partial pressure of oxygen at T prime is less than 1 atmosphere. So, it will try to reduce the oxygen content in the system. So, more oxidation would happen, and since it is a closed system we are not supplying any oxygen from outside or we are not taking any oxygen from inside to the surrounding. So, whatever happens it should happen within the system. Similarly, if it is taken to this particular state is taken to this particular position is taken to this position, then of course, I need more oxygen for the system for the reaction to reach equilibrium, and then more oxygen will come from the reduction of Ag2O. So, this is the very concept of this Ellingham of this particular del G T plot with temperature. Now, this is the Ellingham diagram for that oxide. So, Ellingham diagram is nothing but plot between del G 0 T, which is nothing but RT ln PO2 with temperature for different oxides. Now, in this case one important factor is we are considering all the time PO2, that means 1 mole of oxygen when it is consumed for the oxidation of a pure metal and going to form pure metal oxide. Now, for example, if I consider M plus O2 equal to MO2, that time it is very straightforward, would be equal to RT ln PO2. Now, if it is M plus O2 equal to 2 MO, so that time we will consider like this. So, then also it will become, now if it is so that time we will consider this one as so, I will consider that way. Just a minute, 4 by 3 and yes. So, it will be like this. So, that time also it becomes PO2, and if I plot make it as M1, M2, M3, sorry, if I put it that way then it will be confusing. So, I can say that this is M prime metal, M double prime metal, L triple prime metal. So, this is prime, double prime, triple prime. So, that means M prime, M double prime, M triple prime all are different metals. So, now if I try to plot del G T with temperature for all three cases, I will get a plot like this. I am just drawing arbitrary plot. Okay. And interestingly, if this is for M prime, this is for M double prime, this is for M triple prime, I could see that they are almost parallel to each other. So, that means they have some slope which is nothing but del S 0, that is the slope for every case. Here also del S 0 minus, here also minus del S 0. Now, if I try to calculate their corresponding del S 0, in this case it will be let us say this is equation 1, this is equation 2, this is equation 3 reaction. So, case 1 del S 0 would be equal to S 0 M S minus, sorry, this will be product MO 2 S minus S 0 M minus S 0 O 2 Z, which I can write as this. Case 2, for the equation 2, I can write del S 0 equal to S 2 S 0 M O S minus 2 minus S 0 O 2 gas, which will also become del S 0 equivalent to minus S 0 O 2 gas. So, I could see that, so their slopes, and similarly third case minus S 0 O 2 gas. So, this also becomes del S 0 is almost equal to. So, now you could see that these quantities, this entropy of solids, whether it is 2 by 3 or 2, they will not make much of difference to the overall entropy change, and overall entropy, since the gaseous gas entropy is very high as compared to the solid entropy, and that is what we can roughly say that all the three cases the slope becomes similar, because all the cases slope is nothing but minus S 0 O 2, which eventually become plus S 0 O 2, and entropy of a substance is always positive. So, that is what the slopes are almost similar, and that is what if you see an Eulers diagram, you will see that all the oxide lines are parallel, nearly parallel to each other. Now, this is nothing but Eulers diagram. Now, from this Eulers diagram, one can calculate partial pressure of oxygen which is in equilibrium at any temperature. For example, if I consider this line, then at different temperatures I can calculate partial pressure of oxygen by simply noting down those delta G T values at different temperatures. So, I can measure those, I can find those values, and simple calculation delta G 0 T equal to R T L and P O 2. So, this P O 2 is nothing but equilibrium at the temperature of consideration. So, that is one way of calculation of partial pressure of oxygen which is in equilibrium for that oxidation reaction. So, there is one more way to calculate. If you see Eulers diagram, we will see that on the side, the right and the bottom side, we see that there are some partial pressure of oxygen lines, and those lines, if we continue and we find that those lines meet delta G T axis at 0 when T equal to 0 Kelvin. So, that is one way, graphically one way to find out partial pressure of oxygen equilibrium in equilibrium at a particular temperature of consideration for any oxidation of metal. So, that part we will do in our next lecture, and also in the next lecture we will show how to what is the logic behind getting those radiating line from delta G T equal to 0 at T equal to 0 Kelvin, and then wherever that line crosses any of the oxidation lines, and that crossing point is the partial pressure of oxygen for that particular oxide line at that temperature where it crosses. So, we will do that in our next lecture. So, let us stop here. We will continue our discussion on Illingham diagram and try to see a complete Illingham diagram plot and understand how to read Illingham diagram, and also we will understand what is the importance of Illingham diagram. Thank you very much.